Here I'll be demonstrating the geometry optimization process of a tri-bracket part that was saved in a JT format and imported into Simcenter 3D. I will start with a baseline analysis by creating a new FEM and simulation. I'll then create a new linear static solution and accept all the defaults. I'll then move into the idealized part, which is an associative copy of our master geometry. And once promoted, all the changes to the part will be translated to the FEM in the sim. Here I'll be using the Edit Cross-Section tool to create a set of expressions to be used for the geometry optimization process. I will select the faces of the cross-section that I would want to edit, as well as the plane of the cross-section that we would want to create. Once in the Edit Cross-Section, I can create my expressions for the part. The vertical leg I'll create as T1 and set that equal to 15 millimeters. The second leg is the support leg, which I'll call T2 and set that equal to T1. Next, I will set the horizontal leg to be T3 and have that equal to T1. Any changes to the first leg will also make changes to the other two legs. And lastly, I will add a expression to the base of the part where the support leg intersects the vertical leg. And I'll name that H1. Once finished, the cross-section will update accordingly, and so will the idealized part. Next, we can move into the FEM, and the polygon body at this point will be updated. And I will start by adding a 3D tep mesh to the part and selecting a material from our predefined material list. Then in the sim, I can create loads and boundary conditions for the part. I'll start by creating a pressure load at the very top face of the part. Next, I will create a fixed translation constraint along the back face of the part. At this point, I can go ahead and solve the model. However, to show that the geometry is associative throughout, I will now substitute a new JT file that has updated geometry for the existing JT file. I'll start by saving the model and then closing out of the original part. Once in the File Explorer, I'll rename the original JT file that we used to create the part file as something different, and rename the updated JT file as what the original file was. Once back in the sim, I can then upload the new part and go back into the idealized part. At this point, we can see the geometry has been updated accordingly with the new geometry. You can check to make sure all the expressions we made before are still associated with the geometry. And we can also go back into the FEM to make sure the mesh has been updated. The polygon body has been updated. In the sim, we can see that the boundary conditions and the loads that we applied are still associated with the geometry. At this point, I can go ahead and solve the baseline analysis that will be used for the geometry optimization process. Once complete, the results are then loaded into the post-processing navigator. In this example, I'm going to take a look at the vertical displacement results, which has a displacement of 0.48 millimeters. For this example, I'm going to be creating a new geometry optimization process to minimize the weight of the part by varying the expressions that we created earlier and constraining the model in the vertical direction to no more than 1 millimeter. Now we'll open the geometry optimization tool where we can set up our geometry optimization analysis. First, we'll define our objective, which is to minimize the weight of the part. Next, we can add the constraints that we want to make to the model. I'm going to be constraining the model in the vertical direction to no more than 1 millimeter. Next, we can add our design variables, which would be our expressions we created earlier. At this point, I'll set upper and lower limits to the height of the support and to the thickness of the part. And lastly, we can set our maximum number of iterations. In this case, I'll leave the default number. The geometry optimization model can be solved, and I will pause the video. Once complete, a geometry optimization spreadsheet will appear that has data about the number of iterations, the weight, the design variables, and design constraints. We can also look at different convergence plots for the minimum weight and the variables. We can also take a look at the results in the post-processing navigator for the new parts. Once loaded, I can compare the baseline vertical displacement results to that of our optimal part. In the post-processing navigator, we can see that we can look at results from each design cycle. By laying them side by side, we can see the part has got thinner and also the support height has changed. At this point, if we are satisfied with the results, I can go ahead and save out the new geometry. And that concludes the demonstration.